Evolving dark energy and the case for constraint-driven cosmology. The lambda CDM model, the prevailing cosmological framework, rests on the assumptions of homogeneity and isotropy, where dark energy is considered a constant force, uniformly driving the accelerated expansion of the universe. Yet, recent findings from the Dark Energy Spectroscopic Instrument suggest that the universe's expansion rate may have been slightly faster around 7 billion years ago. This observation hints at the possibility that dark energy is evolving, changing over time rather than remaining fixed. If true, this challenges the core assumptions of lambda CDM and invites a deeper reconsideration of how we understand cosmic time, expansion, and observational interpretation. If time is not a uniform, passive background variable, but rather an emergent parameter shaped by relational constraints, then the foundations of the standard model must evolve accordingly. In quantum physics, measurement outcomes are not detached readings of an external reality, but are shaped by the relational context of the system and the observer. This principle extends to cosmology. The way we interpret redshift data, gravitational lensing, and cosmic structure surveys is not neutral. It is conditioned by the observational constraints embedded in our instruments, assumptions, and cosmic vantage point. If dark energy appears to evolve, we must ask, is this evolution intrinsic to space-time? Or is it a function of how our observational methods resolve and encode large-scale cosmic data? Is the perceived acceleration of the universe a fundamental property? Or is it the result of constraint-driven resolution, where observed expansion emerges as a relational effect, much like the collapse of a quantum state in measurement? This introduces a more layered perspective, where dark energy is not necessarily uniform or universal, but may vary according to gravitational environments, large-scale structures, and temporal constraints. Conceptually, we might visualize this through a converging network or compressed region of space-time, where multiple observational threads resolve into a structured focal point, not revealing a single truth, but manifesting a constrained perception. Within this interpretive landscape, LCDM is not collapsing, but evolving. If dark energy is shown to change over time and space, then the standard model may need to extend beyond its initial assumptions. This does not mean discarding the successes of LCDM, but rather recognizing that its foundation, particularly the use of a constant lambda and a globally homogeneous time, is insufficient to explain emerging data. A paradigm shift is underway, not a revolution against past models, but an evolution towards one that incorporates anisotropies, inhomogeneous constraints, and structured temporal dynamics. Evolving dark energy implies that cosmic expansion may not be directionally uniform. This supports a growing body of observational evidence, such as anisotropies in the cosmic microwave background, bulk flows, and regional variations in redshift measurements that suggest cosmic expansion is not perfectly isotropic. If inhomogeneous constraints, differences in local gravitational potential, matter density, and structure play a role in shaping how expansion unfolds, then different regions of the universe may experience time and acceleration differently. This challenges the assumption that a single global timeline can describe the universe's dynamics. If dark energy evolves and varies across space, then time cannot remain an untouched universal backdrop. Rather, time must be reconsidered as a structured parameter, shaped by the local dynamics of energy, mass, and geometry. In this view, time is not a linear, absolute continuum, but a relational construct that resolves through constraint-driven interactions. This aligns with models such as timescape cosmology, which propose that observers in different gravitational environments experience different temporal flows, even as they share the same broader cosmological history. The Friedmann-Lemaitre-Robertson-Walker (FLRW) metric, which underlies LCDM, assumes large-scale homogeneity and isotropy in the structure of the universe. However, evolving dark energy and observed anisotropies suggest that these assumptions may no longer hold. If expansion is directionally dependent, and time evolves differently across space, then the FLRW model must be revisited. Cosmology may require a new framework, one that accommodates locally structured evolution, gravitational constraints, and a non-uniform passage of time. Such a model would better reflect the relational, encoded nature of cosmic behavior, rather than imposing an artificial uniformity onto a dynamic and varied cosmos. The emerging cosmological picture suggests that dark energy, time, and expansion are not governed by static global constants, but are dynamically interwoven within a field of structured constraints. Rather than being overturned, the standard model is being extended. A new cosmological paradigm is taking shape, one that embraces anisotropies, evolving energy fields, and the relational encoding of space-time. In this framework, cosmic acceleration is not an absolute fact, but a resolved phenomenon, shaped by how we observe, where we observe, and the deep structure of the universe itself. Such a perspective demands that we move beyond the assumption of homogeneity, not to discard it, but to enrich our understanding of cosmic order through constraint-driven, emergent models of time and space. The next chapter of cosmology will be one where measurement, perception, and relational dynamics converge to reshape our understanding of the cosmos. Here is a conceptual visualization of evolving dark energy, depicting the mysterious expansive force as rippling cosmic currents and distorted space.